Let's continue from where we left off. Last we left off, we had the, actually we're supposed to be using the Leibniz notation. So dy by dx we found was minus 9.8 x, and that was plus 10. Okay. So in the next part, we were supposed to evaluate dy by dx for when x is equal to 3, I believe. So what we're going to do is replace the x with 3 and evaluate it. Okay. Just use this with 19.4. And because this is a real quantity, or we're given a model of such, we're going to say we're going to give units to it. And I think it's in meters per second. Okay. Meters per second. And what does that mean? That means that in this case, the rate of change, so it's going to be actually velocity if you want to write that, or the rate of change, if you're more comfortable writing velocity, of the javelin at 3 seconds is minus 19.4 meters per second. Okay, and that would be a final answer. In example number 4, we're asked to differentiate the function y is equal to 1 over x. Express the derivative using Leibniz notation. Okay, let's look at this question. Okay, so our function f of x is equal to 1 over x, and we are asked to find dy by dx. Okay. Now, let's see, can I do something with this? Well, I can change that to make it look a little bit nicer for us. Actually, we don't need to do that quite yet. Let's just use it as it is. And from first principles, again, I'm going to write it out. And after this unit, once you finish your test, no, you don't have to use first principles until you get to the exam, okay? And then I'll teach you some new techniques. Let's see now. Using our function, let's plug it in. Okay, sure, let's use some square brackets. 1 over x plus h. Remember, wherever there's an x, you're going to replace with x plus h. You're going to tack on that little h there, okay? Minus 1 over x all over h now. Okay? All right, so the limit as h approaches 0. Okay, so I can just remove the brackets. X plus h minus 1 over x all over h. Okay, so the first thing I'm going to probably do is when I see something like this, you've got fractions in the numerator, it looks really improper. So what I try and do is I'm going to come up with a common denominator and simplify that a little bit more. So the limit as h approaches 0, so the common denominator in this case would simply be x times x plus h. Okay? Let's see now. X, you have to multiply the numerator by just x, minus, and then the second term here will just be multiplied by x plus h. So x plus h. Then I put that in brackets so that I don't forget to multiply that in. Okay? Don't forget that's all over h. Quite sloppy, yes. But we will simplify this to make it look much nicer than that. So the limit as h approaches 0, okay, x minus x minus h, okay, all over x squared plus xh all over h, or what we can do is, so I just want to start the side note again. Now say let's take, for instance, if you had something that was, I'm just going to make this up, x squared over h. Okay, so this fraction symbol is the same thing as saying divided by. Okay, so if we wanted to actually simplify this in a different way, we can simply say x squared, and the rules of division for fractions is that we're going to multiply. Remember, it's take the division, change it to multiplication, and then invert the denominator, which is 1 over h, and that's the same thing. Okay, so what we're going to do over here, let's go back to our question. We're going to go multiply by 1 over h, okay, just to make it look a little bit nicer. All right, let's get a piece of paper. Okay, so what we have now is the limit as h goes to 0, and we're only left with just negative h all over x squared plus xh, okay, times 1 over h, and we can cancel these, okay, and we didn't have to do this because it would still be the same if we left it over h, but I thought this might be easier to look at, okay. So now let's rewrite what we have left, which is negative 1, okay, so that just gives us negative 1 times 1 is negative 1 x squared plus xh, okay. Let's evaluate the limit. The limit as h approaches 0 of negative 1 over x squared plus 0, and now we have, actually we can get rid of this and finish with that, negative 1 over x squared. So that would be our derivative, okay? We just have one more thing to take care of, and that is checking your learning. Which of the following does not provide the exact value of the instantaneous rate of change at x is equal to a? And explain. Okay, so you're going to make your choice right now. And the answer in this case is C. And the reason is because this gives you the slope of the secant rather than the instantaneous rate of change. For the exact value of the instantaneous rate of change at x is equal to a, you would need a derivative or the limit. So we need a very small interval for us to have more of an exact estimate or the exact value of the instantaneous rate of change. That concludes our lesson for today, and we'll see you next time.